My name is Steve. This is my face, and I'm going to be talking about some of the realistic rendering work that we've been doing at Facebook Reality Labs. So the goal of this work is to create a social VR system that gets as close to real-life interactions as possible. Human beings are social creatures, or so I'm told, and to be able to have an authentic conversation with another person is sort of at the core of the human experience. Enabling authentic social interactions across distances would have a huge impact on our lives, and importantly, we want the system to work for everyone in the world. Now, a big challenge of enabling authentic social VR is creating really high-quality photorealistic avatars. So last year at SIGGRAPH, you may have seen Meet Mike. Meet Mike is a state-of-the-art photorealistic avatar created from a compendium of different companies to enable real-time social interaction in VR. And the project was a huge leap forward for facial realism and virtual humans, and it's no surprise that it took a very large team to be able to create this avatar. Mike's avatar is a traditional face rig built by a team of artists. This is a difficult process because artists must define the parameters of a physically inspired model of the skin, hair, eyes, mouth, and how those objects interact with light. The complexity of the interaction between light and geometry means that the artists need to spend a lot of time, generally manually tweaking the parameters before they arrive at a realistic, animatable avatar, and at the end of the process, you only get one rig. For this reason, it's kind of difficult to scale this sort of model to billions of people. A few decades ago, an approach called active appearance models were developed to display and track faces. Now, active appearance models represent the face as a joint linear model of appearance in the form of a texture map and shape in the form of a mesh. So in other words, as the geometry deforms, the texture changes. So if I raise my eyebrows, my forehead gets wrinkly, that's modeled by the texture. So the AAM can capture the sort of correlations between these geometry and the texture. And although the model has coarse geometry, the texture is able to compensate by filling in details, for example, inside the mouth. AAMs avoid a comprehensive physical model of light interaction and facial appearance in favor of a generic, more data-driven approach. This means that it's more automatic and to create and can work when the assumptions of a physically inspired model don't hold. And for these reasons, we believe that AAMs might provide a better path than traditional face rigs for scalable photorealistic face rendering. So if we were to build a 3D AAM, we would start by tracking the face with a mesh. We can use that mesh to unwrap an appearance texture map, and then we would perform principal component analysis to reduce the dimensionality of the data into a small set of parameters that control the facial expression. And when we want to render the face, we take those animation parameters, we reconstruct the appearance and the shape, and then we can just rasterize that to the screen. Unfortunately, AAMs don't account for the way viewpoint affects appearance. So the most obvious way that view-dependent effects come from, like specularities, due to the interactions of light with the surface of the face. But the relationship between viewpoint geometry and texture is actually a little more complicated than that. If the track geometry is inaccurate, then the viewpoint has a strong nonlinear effect on the texture map. To kind of break that down and explain what I mean, let's look at the appearance of the face as we change viewpoints. So here I have 3 different viewpoints of a person's face. We have this track geometry. We can use that to unwrap 3 different texture maps from each of the viewpoints. These are view-dependent texture maps. So, I mean, the most obvious thing is that they're missing large portions of the face. That's because that face is part of the face is not seen from that particular camera. You can also see some intensity differences on the more oblique angles. That's because of specularities. So if we take a closer look and I want you to pay in particular attention to the teeth here, you can see that they're actually in different positions of the face, or different positions of the texture map. This is because the mesh model that we're using doesn't actually have geometry inside the mouth. It's simply a set of triangles that stitch the lips together. So in regions where the track geometry is incorrect or inaccurate, the appearance will slide along the texture map as the viewpoint changes. And if we try to represent geometry and texture with a linear model, we'll end up with either not being able to represent this kind of behavior well, or we're going to have to use an extremely large number of bases to represent it, which will incur a really high computational cost. So recently, there have been a popular approach to learning nonlinear functions. Some of you guys may have heard about it. It's called deep learning. GANs are a pretty popular approach for modeling nonlinear image generation. The images I'm showing here are from progressive GAN. It's a pretty recent approach from NVIDIA. Random vectors are fed into this generator network, which outputs really high quality face images. So these deep networks are able to model really complex appearance behavior of the face under different lighting, different viewpoints, different identities and expressions with these complex nonlinear functions. However, we can't really use these results directly because they're just 2D images. We can't composite them into like a 3D scene because they don't really follow the traditional graphics pipeline. However, we can use deep models to represent the nonlinear behavior of view-dependent texture. So in this work, we use an autoencoder to do that. An autoencoder is a machine learning model that uses an encoder network that transforms the input, in this case, appearance and mesh, into a compact latent representation. And then you use a decoder network to decode that latent representation back into your input, your appearance and shape. So to model the change in appearance due to viewpoint, what we do is we condition the decoder on the viewpoint of the texture map by including it as a separate input. This allows the latent representation to control the facial content, which is like the facial expression, eye gaze, everything like that, while allowing a virtual viewer to view the face from different angles through the viewpoint conditioning variable. To train this autoencoder, we minimize a loss function that consists of 3 terms. So the first term is the reconstruction of the appearance texture. So capital T here is texture, little t is the time instant, V is the viewpoint. So it's an L2 loss. It's actually weighted L2 loss. The reason why we weight it is because were those large regions where we didn't actually see any face texture because the face was occluded. We don't want to penalize that in the reconstruction. The mesh, the second term is a little bit simpler. It's just the reconstruction of the mesh vertex positions. The final term is the regularization term of the variational autoencoder. This term encourages the latent representation to be as compact as possible, which helps disentangle the latent code from the conditioning variable. The reason why it does this is because it tries to minimize the difference between the distribution of latent values and a standard normal distribution. So if the Kale divergence term goes to 0, then the latent encoding contains absolutely no information about the input and will reconstruct the inputs poorly. The network is penalized from including any viewpoint information in the latent representation because we provide it as the conditioning variable. So this encourages this disentangling behavior, which is going to be useful throughout this whole work. So actually in practice what we do for disentangling just with respect to viewpoint is to average the texture maps across viewpoints and input that average texture into the encoder. This way we get sort of a perfect disentangling. The latent representation doesn't encode any viewpoint information at all, so that our decoder will work correctly. This only can work for viewpoint, and I'll talk about other variables we may want to condition on later where the disentangling behavior I just talked about is useful. So the decoder architecture here consists of 2 inputs. The first is a latent encoding vector that represents facial content, and the second is the viewpoint. It has 2 output branches. The first is the mesh vertex positions. There are 7,000 vertices for a total of about 22,000 floating point values. The size of the encoding vector is only 128 dimensions, so it's a pretty small, very, very compact representation of the facial content. The first branch consists of 2 fully connected layers, and it produces the mesh vertices from the encoding. The second branch concatenates intermediate representations of encoding and viewpoint together and uses a series of Scheidt transpose convolutions to create the appearance texture. So the final output of the appearance texture is 1K by 1K. This decoder actually does run in real time at over 90 Hertz on a GeForce 1080. The reason for this is because even though there are a lot of convolutions, the most expensive ones are at the end, the 16 channel and the 3 channel. And they have few enough channels that it still manages to run in real time. One trick that we actually use in this architecture is to have per pixel biases for each of the convolutional layers. Because many pixels in the texture map stay fixed, this helps us model those the fixed regions much better. So I just want to show some renderings that demonstrate the quality of these avatars visually first, so you get a sense of it. So here I'm showing a real image, like a real video that we captured on the left, and then the rendered avatar rendered from the same viewpoint on the right. So the biggest difference that you want to look out for is inside the mouth.
Purebred poodles have curls. The treetop waves in a graceful way.
I promised floating heads reading weird sentences, and I delivered. Remember that the geometry in the texture were produced from a 128-dimensional encoding, so this is actually like a huge compression of what your face is doing. In case you're wondering, by the way, the green stuff around his ears are just headphones. So in this example, take a look at the facial hair. So we're not modeling any hair geometry at all. This is all the texture.
Mine was spattered on the front of his white shirt. The cigar burned a hole in the desktop.
So our model can model these sort of complex behaviors like sticky lips just automatically directly from the data. So next I'll show the camera pan around so that you can see that this model actually does interpolate well when we change viewpoint.
We frown when events take a bad turn. Port is a strong wine with a smoky taste.
So keep in mind that the inside of the mouth is being represented entirely by a texture map, and that gives the impression of depth inside the mouth, even though there isn't any.
The young kid jumped the rusty gate. Guess the results from the first scores.
So there are two really important questions about this work, about this model. And the first is, how accurate does the geometry need to be for this model to work well? And the second is, how many viewpoints are needed? And it turns out that these questions are actually interrelated. So we set up an experiment where we degraded the geometry that we use in the model in a few different ways. So on the right is the model that we actually use for tracking. It looks like this. It has about 7,000 vertices. To the left of that is a version where we smooth the vertices so that the fidelity is a little bit less. To the left of that, we have a static ellipsoid. And then finally, the most coarse model we have is a 2D billboard. So the results that I've been showing are all with this tracked mesh on the right and 32 or more viewpoints. And we get results like this. So what happens if the geometry is too inaccurate? So if we use this billboard, we can see that the model is no longer able to interpolate between viewpoints. Okay, what if we use the high quality geometry, but fewer viewpoints? Things look pretty good here, but if you take a close look at the inside of the mouth, you'll see the teeth kind of switch at a certain point, and it looks weird. So the conclusion from this experiment is that as your geometry gets coarser, you need more viewpoints to make up for that difference. And if your geometry is as coarse as just a single image, you need many, many viewpoints. More than we have. So I've described the system for creating realistic avatars, but so far they just repeat what they've done during the capture system. So we developed a system to animate these avatars from cameras mounted on a virtual reality headset. So to do this, we created a headset, you can see it in the bottom left, with some cameras inside that point at the eyes and mouth. They produce images like the ones on the left. You can see it's kind of an oblique view of the eye, and you see just the lower mouth. What we want to do is produce an animation like the one on the right. So if we had headset images for each of those latent encodings that we had, then we can train a neural network to map from headset images to latent encoding. But the problem is we can't collect that data because if you wore the headset while you were in the multi-capture system, then we wouldn't be able to build a good avatar. So to get around this problem, what we propose is to generate these headset images synthetically. So we want to create synthetic headset images like these. And like I mentioned, we want to use our multi-camera image data. So what we can do is just simply perform image-based rendering. We have the geometry, we can approximate where those headset cameras would be on the face, and then we can just apply a warp to get these synthetic headset images. So problem solved. Unfortunately, the synthetic images don't really look like the real images. Like if you look closely, you can see that the eye images in particular look much different. Part of this is because the real headset images use IR cameras and the multi-camera system is RGB. There's also a background in the face images. So if we try to learn a system that regresses from our synthetic HMD images to that latent code, then we're not going to get good results. So the solution to this problem is to do some domain adaptation. And we use variational autoencoders again to do this. So we build a variational autoencoder, another one. We feed in sets of real and also synthetic HMD images. And this variational autoencoder is going to disentangle and automatically find a common representation of facial expression for us. Then we can learn a simple linear transformation between that headset, the modality invariant headset code, and our avatar rendering code. So when we look at the complete pipeline, this is what it looks like. We take our headset images, we encode them into this headset code, we linearly transform them into this avatar code, and we just plug that right into our avatar decoder, where the viewpoint is conditioned based on an external observer. So here are some visual results of our method. So on the left, we have the real headset images. On the right is the decoded and rendered avatar.
Purebred poodles have curls. Treetop waved in a graceful way.
On the blotter was made by green ink. Was spattered on the front of his white shirt.
So to conclude, I just want to touch on some of the limitations of this approach and some of the things we've been doing to alleviate some of those limitations. So the first thing is, I talked initially about we really want this to scale to everyone. The problem is each of these models are personalized. So we haven't really proven this out to 1 billion people. The second thing you might have noticed is that the lighting is going to be baked into the model. So the lighting that you were captured in is the lighting that your model has. This was mostly trained on speech data. As you can see, we didn't show many facial expressions. That's kind of a limitation of the data we had. It should work on general expressions, but we just, at the time of the paper submission, didn't have enough data. And finally, hair is still difficult. I'm sure this comes as no surprise to many people that hair is one of the toughest things to render. So I just want to touch on a few things that we've been working on, making this scale to different people, and also working on lighting. So this is an identity condition model. The idea is that we have an additional conditioning variable, the identity of the person. What we've done is encode with that model on the left, the person on the left, and decode with different avatars. And what happens is it automatically learns a common representation of facial expression. So this is an early result, so I don't want you to dig your claws into it too deep, but it's just a first step on the path to how can we make a model that can model everyone. The second thing is about actually making this model re-renderable. So I need to add a disclaimer here that this was not in the paper. This is something that we've done, worked on since then. But the idea is the same as the identity condition. If we have a capture system that can change the lighting environment, we can condition our model on those different lighting environments. So this is a result of changing the lighting environment by changing the conditioning variable that controls illumination. With that, I'm happy to open it up to questions. Thank you.